Hey, good morning class, and welcome to lesson 8.3.3. How can I rewrite the sign of a plus b? And this is part 2. The objective is still the same. Use sum and difference identities to find exact angles that are not standard on the unit circle. And we're also going to today add to that a little bit, and we're going to introduce you to what we call our double angle identities. Using the skills from the previous lesson, you have the sine of a plus b, and that's equal to the sine of the first angle times the cosine of the second angle plus the cosine of the first times the sine of the second. And then you got the corresponding difference formula for sine. The cosine of a plus b is equal to the cosine of the first times the cosine of the second minus the sine of the first times the sine of the second and its corresponding difference formula. And we did not deal with the tangent formulas. Well, let's put these to use just like we ended the last lesson. Let's find the sine of pi over 12. And let's find the cosine of 5 pi over 12. Now, before we do that, I want you to think about the objective, which was to find the sine and cosine of angles that are not on the unit circle. And so I'm going to do some work here for you, and then we'll come back to answer these questions so that you actually see what we're trying to find. Here is our unit circle. And on our unit circle, you know that you've got this angle right here. We're going to call that pi over 6. And pi over 6 is the square root of 3 over 2, comma, 1/2. And up here, you've got pi over 3 for an angle. And there's pi over 3. Its coordinates are 1/2, comma, square root 3 over 2. And we also know that the x-coordinate is always going to be the cosine of our angle, comma, the sine of our angle. So we also know then that the cosine, should probably use a highlighter for this, the cosine of pi over 6 is square root 3 over 2, and the sine of pi over 3 is square root 3 over 2. So we know that then the cosine of pi over 6 is the same as the sine of pi over 3, which in reality is part of a property that says the cosine of theta is equal to the sine of pi over 2 minus theta. And so the cosine, or not so, that is why the cosine of pi over 6 is equal to the sine of pi over 2 minus pi over 6. Which is the sine of pi over 3. That's why these come out to be equal mathematically right here. Geometrically, they're equal because this x-coordinate right there is the same as this y-coordinate. Now let's take all of that and apply it to the angles that we have up here. So I'm going to draw another unit circle. And on this unit circle, obviously this is 0. This is obviously pi over 2, but let's write that in terms of 12ths because our denominator here is 12. Let's call this, in terms of 12, 6 pi over 12. Therefore, if I have pi over 12, which would be maybe right about there, then 5 pi over 12 is going to be right there. This angle here is going to be 5 pi over 12. Which, if I'm looking at this correctly, would really be the same as 6 pi over 12 minus a pi over 12. So if I use this property that we just talked about, if I take and use the sine of pi over 12 is going to be equal then, I don't want to write it like that. I guess it's not that previous property, it's just a property very similar to it. So if I have the sine of pi over 12, that has to equal the cosine of 6 pi over 12 minus pi over 12, or the cosine of 5 pi over 12. Now, that's mathematically kind of our little proof that we know that these two answers that we have up, or two questions that we have up here, part C and D, they're going to be the same answer. The sine of pi over 12 is going to be the same as the cosine of 5 pi over 12. Geometrically, that's because the sine, which is this distance, is going to be the same. In other words, so the sine of pi over 12 is going to be the same as this x-coordinate up here for 5 pi over 12, which is the cosine of 5 pi over 12. So all of that's going to be the same. Now, we just need to find the sine of pi over 12 and the cosine of 5 pi over 12. Sorry, I just slide this around. I got so excited talking about that stuff down there, I completely forgot to leave room to actually solve these. So the sine, the sine of pi over 12 equals, well, I need to take that pi over 12 and split it into two angles. Let's go with, since it's 12, let's go with something in terms of thirds and fourths. So if I was to take maybe 4 pi over 12 and subtract from it 3 pi over 12, that's going to give me a pi over 12. Well, these are really the same as the sine of pi over 3 minus pi over 4, which then is equal to, using our property down here, the sine of the first angle times the cosine of the second angle minus the cosine of the first times the sine of the second. We know that the sine of pi over 3 is the square root of 3 over 2. The cosine of pi over 4 is the square root of 2 over 2 minus the cosine of pi over 3, which is 1/2, times the sine of pi over 4, which is the square root of 2 over 2. And this simplifies down to everything's going to be over 4. The square root of 3 times the square root of 2 is the square root of 6 minus 1 times the square root of 2 is the square root of 2. So this is the y coordinate for the sine of pi over 12. Let's take a look at, or have you do, and then you can come back to this, find the x coordinate for the cosine of 5 pi over 12. Now, we already talked about that. This y coordinate for pi over 12 has to be the same as the x coordinate for 5 pi over 12. So yeah, you could say, well, it's going to be the same. I'm just going to write that answer down. The point isn't to get the answer. The point is to understand what we're talking about here, but also being able to use your angle sum and difference identities. So I'm going to find a spot down here and have you pause this to do the work and then come back and check your work with my answer. Okay, welcome back. What we have here is the cosine of 5 pi over 12. That is equal to, one way to write it is 8 pi over 12 minus 3 pi over 12. Simplify those down and you have the cosine of 2 pi over 3 minus pi over 4. Then using your property up here, the cosine of the first angle times the cosine of the second angle, so the cosine of 2 pi over 3 times the cosine of pi over 4 plus the sine of the first angle times the sine of the second angle. Well, the cosine of 2 pi over 3 is a negative 1/2. Cosine of pi over 4, square root 2 over 2. The sine of 2 pi over 3 and the sine of pi over 4. Now, if you multiply those together, negative square root 2 plus square root of 6, which is the square root of 6 minus the square root of 2 over 4, which is the exact same thing we had up here for the sine of pi over 12. So they did come out to be the same. One last thing to emphasize is this is just one way to write the sum or difference for 5 pi over 12. Oops, I didn't want to scribble that out. For 5 pi over 12. You could have chose other angles. 5 pi over 12 could also be, so 5 pi over 12 could also be written as 2 pi over 12 plus 3 pi over 12. Which then, another way to write it would be, you could have the cosine of pi over 6 plus pi over 4. You could have done that instead of using the angles that I happen to choose. And there are others. Now, what we'd like you to do next is to use these to come up with some other trig expressions. So if I have the cosine of pi minus theta, what is that going to be equivalent to? Well, let's use our sum and difference identities. The cosine of the difference of two angles is equal to the cosine of the first angle, cosine of pi, times the cosine of the second angle, theta, plus the sine of the first angle times the sine of the second angle. Well, the cosine of pi is a negative 1 times the cosine of theta, plus the sine of pi is 0 times the sine of theta. And we know 0 times anything is 0. So the cosine of pi minus theta is equal to, what do we get here? A negative cosine theta. Those are equivalent expressions. Now what we'd like you to do is try one of these on your own. Find the sine of theta plus pi. Pause this and then come back and check your work. And welcome back. The sine of pi plus theta is equal to the sine of the first angle times the cosine of the second plus the cosine of the first times the sine of the second. Look up on the unit circle. Cosine of pi, that's -1. The sine of pi is 0. We know that 0 times anything is 0. So we just end up with a negative sine theta. Well, that pretty much wraps it up for lesson 3.3. Let's just dabble a little bit into lesson 3.4. What if I double the angle? Your objective today is to learn just a little bit about the double angle formulas, and we're going to take a few minutes to derive those. The double angle identity for sine is derived directly from the angle sum identity for sine of a plus b. So in part A, we want to rewrite the sine of 2a so that you can use the angle sum identity to help solve for that. So I'm going to rewrite this as the sine of a plus a, because a plus a, this right here, is 2a. And that's equal to the sine of a times the cosine of a plus the cosine of a times the sine of a. Well, I have a sine a cosine a, and here I really have a sine a cosine a. So this is equal to 2 of those. 2 sine a times the cosine of a. And we started out originally with the sine of 2a. This is what we call a double angle formula for sine. The sine of doubling an angle. So if a happened to be 30 degrees, the sine of 30 times 2, or the sine of 60, is equal to 2 times the sine of the angle times the cosine of the angle. Let's do the double angle identity for cosine. And it can be derived using the method we just employed in problem 130. So let's rewrite 2a as the cosine of a plus a. That's equal to, now using our angle sum identity, cosine of a times the cosine of a minus the sine of a times the sine of a. Well, cosine times cosine is cosine squared a, minus sine times sine is sine squared a. Therefore, the cosine of 2 times angle A is equal to the cosine squared of A minus the sine squared of A. This happens to be your double angle formula for cosine, or at least one of the double angle formulas for cosine, because we can take that expression and rewrite it using our fundamental Pythagorean identity. If you recall, this identity is cosine squared a plus sine squared A equals 1. Or another way to write that was if I subtract sine squared from both sides, the cosine squared of A equals 1 minus the sine squared of A. Or if I take what's up here and, whoops, sorry about that. If I take what's up here and subtract a cosine from both sides, or cosine squared from both sides, then I get sine squared A equaling 1 minus cosine squared A. So let's take this first statement, and I'm going to replace my cosine squared up here with 1 minus sine squared. So my new statement would be cosine of 2a. So I'm starting out here. Cosine of 2a. I started out with this equals. Now I'm going to replace this with 1 minus sine squared. 1 minus sine squared a. Now I still have a minus sine squared a. So then I'll minus another sine squared a. That gives me 1, and I've got 2 minus sine squareds. So minus 2 sine squared a is the same as the cosine of 2a. Let's do something similar, but let's take 1 minus cosine squared and put that in for sine squared. So starting out again, cosine of 2a equals, I have a cosine squared a minus, I'm going to subtract from that a 1 minus a cosine squared a. Now I'm going to have to distribute that minus sign. So this is still a cosine squared a. I'm going to go minus a 1. Then we're going to go minus a minus. So that's plus cosine squared a. And I now have 2 cosine squared a's. Minus 1. That's the same as the cosine of 2a. This gives you 2 more properties. Sorry about the pause there. Or 2 more identities. So from your work over the last few slides, we have double angle identities. The cosine has 3 versions of its double angle identity. It can be equal to cosine squared a minus sine squared a, 1 minus 2 sine squared a, or 2 cosine squared a minus 1. In your sine squared, or sine of 2a, formula from the previous slide, the sine of 2a is equal to 2 times the sine of a times the cosine of a. There's only one of those. Here are those double angle identities for sine and cosine, and we are not developing these this particular year, half angle identities for sine and cosine. Hopefully you enjoyed this lesson. Please talk to your teachers about how to show some of these identities or prove these identities during office hours, or send an email to them. Everybody, wishing you the best for this upcoming weekend, and enjoy your time with family and friends.